Hello, students. Today, we are going to make a very important topic in chemistry simple and clear for you. We will be discussing how to express the concentration of solutions. So let's start with a simple question from our daily life. When someone says a cup of tea is strong or a glass of juice is weak, what does that actually mean? How strong is strong? How weak is weak? It's a bit vague, isn't it? And you see, in science, and especially in a field like medicine, this kind of vagueness can be very, very dangerous. We cannot afford to be imprecise. Saying a medicine is strong is simply not enough. We need to know exactly how much of the drug is present. And this brings us to our first key idea, the problem of quantifying how much. How do we go from these everyday vague words to precise, universally understood numbers? Let's take a real-world example to understand this. Look at this IV drip from a hospital. On the label, it says 5% W/V glucose. Now, this is not just a suggestion. It is a very precise medical instruction. It means there are exactly 5 grams of glucose for every 100 milliliters of the solution. Getting this number right is not just about good chemistry. It is absolutely critical for the patient's safety. In fact, it can be a matter of life and death. So, chemists needed a precise language to talk about concentration. But as it turns out, there isn't just one language. There are actually several, and each one is useful in different situations. At the most simple level, concentration is just a ratio. It tells us how much solute, that is, the substance being dissolved, is present in a certain amount of the solvent, or in the total solution. It's a very simple idea, really, just the amount of stuff in a certain amount of space. Now, here's a wonderful analogy to help you remember this. Expressing concentration is like trying to measure the density of a crowd. Imagine you walk into a crowded room. You wouldn't just say, "Oh, it's crowded," right? You would want to be more specific. So how would you actually measure that crowdedness? Well, there are different ways, you see. We could count the number of people per the entire theater, the whole room. This is just like molarity. Or we could count the number of people per the area of the floor space only, ignoring everything else. This is like molality. We could also calculate what fraction of the crowd are, say, women. That is like mole fraction. Or we could simply say what percentage of the room is filled with people. That's like percentage. So you see, 4 different ways to describe the exact same crowd. Okay, so let's put this idea into practice now. We are going to make one single solution, and then we will look at it through all 4 of these different lenses to see exactly how they give us different numbers and different perspectives. Right. First, let's imagine we are in the chemistry lab. We take exactly 1 mole of salt, which you know is 58.5 grams of sodium chloride. Then, we dissolve the salt in 100 grams of water, which has a volume of 100 milliliters. Now, here is a very important point. When we dissolve the salt in the water, the final volume is not exactly 100 milliliters. Why? Because the salt ions themselves take up some space. So for our calculation, let's just say our final solution volume is a little more. Say 105 milliliters. Please remember this number. All right, let's apply our first lens, molarity, which we write with a capital M. Now, molarity always focuses on the total volume of the solution. Remember our analogy? This is like people per theater. We are measuring based on the entire space. We know that molarity is the number of moles of solute per 1 liter of solution. So we take our 1 mole of salt and we divide it by our total volume, which is 0.105 liters. This gives us a molarity of about 9.5 molar. Now, let's switch to our second lens, molality, written with a small m. Molality is different. It completely ignores the total volume. It only cares about the mass of the solvent, the water we started with. This is like people per acre of floor space, where we are only measuring the floor. So we used 100 grams of water, which is 0.1 kilograms, and molality is moles of solute per kilogram of solvent. So it is simply 1 mole divided by 0.1 kilograms, which gives us 10 molal. Now just notice, for the very same solution, we have 9.5 molar and 10 molal. The numbers are different. So this is the crucial difference you must remember. Molarity uses the total solution volume in its denominator. Molality uses only the solvent mass. And this has a very big practical implication. You see, molarity can change with temperature because volume expands or contracts, but molality does not change because mass is always constant. This is why scientists who study properties that change with temperature, like boiling points, will almost always use molality. It is temperature independent. This is a very important distinction for your exams. Okay, let's look through our third lens, which is mole fraction. Conceptually, this is the simplest of all. It is just a ratio of the moles of one component, in our case the salt, to the total moles of everything present in the solution. So, we have 1 mole of salt. We also need to find the moles of water. 100 grams of water is about 5.56 moles. So the mole fraction of salt is 1 divided by the total moles, which is 1 plus 5.56. This comes out to about 0.152. And notice, it has no units. It is like saying that 15.2% of all the particles in the solution are salt particles. And finally, our fourth lens is percentage by mass. You will see this very often on industrial products, on medicines, just like that IV drip we saw at the beginning. It is a very simple and practical ratio of masses. We took 58.5 grams of salt and we dissolved it in 100 grams of water. So the total mass of the solution is simply their sum, 158.5 grams. The mass percentage is the mass of the salt divided by the total mass, all multiplied by 100. This gives us 36.9%. So there we have it. One single solution, but 4 different, and all correct, numbers to describe its concentration. 9.5 molar, 10 molal, a mole fraction of 0.152, and 36.9% by mass. Let's just quickly recap the main points that you should remember.
First, always remember that at its core, concentration is just a simple ratio. Second, think of these different units, molarity, molality, and so on, as different lenses or different languages to describe this same ratio. Third, that crowd density analogy is a very powerful way to remember the difference. Molarity is people per theater, molality is people per floor space. And finally, always remember why this precision matters. Just think of that hospital IV drip. So, my advice to you is this. Please do not just memorize the formulas. If you can remember the core idea that it's just a ratio, if you can remember the crowd analogy to visualize the differences, and if you remember the IV drip example to know why this all matters, then I promise you any question on this topic will feel much, much lighter in your exam. You will be able to approach it with true understanding and with confidence.